In this video I'm going to solve every question from the UKMT Junior Maths Challenge from 2020. That's one of the main maths challenges in the UK, usually taken by students aged 11 to 13, but often also taken by younger students as well. And if you're preparing for that challenge, then take a look at my free course, Get Ready for the Junior Maths Challenge. In that course you can practice all of these questions as well as questions from other papers, and each question has a video hint and a full video solution. So you can have a go at the question, then watch the hint if you're stuck. That gives you really the best chance of getting the answer by yourself. Then you can see if it's right and then watch the video solution if you want to. It's a really great way to prepare for the Junior Maths Challenge. Over at the course's website I've got loads more courses to prepare for maths challenges and for school maths as well, so I really hope you will take a look over there. But if you'd like to watch the solutions here on YouTube instead, I'll get on with them now. I'll put timestamps below so you can jump to the questions you need, or if you'd like to work through the whole paper with me here, then we'll start at question 1 and you can pause the video at the start of each solution. Because all of these numbers are smaller than 11 squared, we only need to check whether they are multiples of 2, 3, 5 or 7 to know if they're prime. If they're not multiples of any of those, they'll definitely be prime. Now, we can see none of them are even, so they're not multiples of 2. We can also see easily they're not multiples of 5 because they don't end in a 0 or a 5. Then there's an easy test for multiples of 3, which says add the digits together and see if it's a multiple of 3. So in the first one, 1 plus 0 plus 1 is 2. That's not a multiple of 3, so it's not a multiple of 3. And you can check that for all the others. 1 plus 0 plus 3 is 4, etc. And you'll see if you look at E, 1 plus 1 plus 1 is 3. And so we know actually that one is a multiple of 3, and this is the one that isn't prime. If we hadn't found a multiple of 3, I'd have also had to check for 7. But we found the one that isn't prime, and so that's the answer, E. So here we've just got to work out 2020 divided by 20. I think I'd think of it like this. I would just think, well, I know that 20 times 100 is 2000, so 20 times 101 would be 2020. So I'm not actually doing the division here, and I can do that super quickly in my head and realise that that means the answer is 101. But of course, if you prefer, you could also just write it out like a long division like this, and you'll get 1, 0, and then you'll carry a 2 here, and you'll get 1, and you'll see the answer is 101 that way as well. So we want to know how many of these shapes have rotational symmetry of order 2. That means that when I rotate the shape, there'll be 2 times in a full rotation where it looks the same. So every shape has at least rotational symmetry order 1, because when I come all the way back to the start, it looks the same as where it is at the start. So for rotational symmetry of order 2, there's got to be one other time when I do that rotation that it looks the same as when it starts. Now I've set up the page here so I can just rotate them. So on the first one here, you see if I rotate this, when I go halfway around it looks exactly the same. So that one does have rotational symmetry of order 2. In the second one, if I go around when it's halfway, these lines are at the bottom rather than the top, so that one doesn't have rotational symmetry of order 2. For this one, again, if I rotate it, that bottom line there is going to end up at the top instead of the bottom. For this one, when I rotate it halfway around, yeah, look, that line ends up the same way around, and then I go the full way around. So that one has rotational symmetry of order 2, and the last one, when I get halfway around, it looks the same, and again, when I'm back at the start. So that one has rotational symmetry of order 2 as well. So it was this one, and this one. And the answer, the question is how many of them have order 2, so the answer is 3C. How many centimetres are there in 66.6 metres? Well, 1 metre is 100 centimetres, so to go from 66.6 metres to centimetres I'm going to have to do 66.6 multiplied by 100, so times 10 would make 666, times another 10, 6,660, and so the answer is B, 6660. Let's do this question in 2 ways. Okay, so Amrita thinks of a number, she doubles it, adds 9, divides her answer by 3, and then subtracts 1, and gets back to where she started with. So let's say her original number was x. When she doubles it, it would be 2x. Then she adds 9, we'd get 2x plus 9, divides the answer by 3, so let's write this all as a fraction divided by 3, and then she subtracts 1, and she gets the number she originally thought of. So when we follow this whole process through, that means we get back to x. So I've got an equation here that I could just solve to find out x. So I could multiply it by 3. That would give me 2x plus 9 minus 3 equals 3x. Remember, I'm multiplying the whole of the left-hand side by 3 and the whole of the right-hand side by 3. So that means I need to multiply every single term by 3. And 2x plus 9 over 3 times 3, well, that's like dividing by 3 and timesing by 3, so it cancels out. And I just remember I've also got to multiply the minus 1 by 3 and the x by 3. Now we can say now 9 minus 3 is 6, and if I subtract the 2x from both sides, I get 3x minus 2x over here, and so x is equal to 6, and that must have been the number. So another way of doing this question, because it's a multiple choice question, we could have just checked them. So I could have gone through and said, well, 1 times 2 plus 9 is 11, then I get 11 over 3 and I subtract 1, well that's not 1, right? And I could just very quickly check that for all of the answers here, because I know one of these has to be the answer. You would also be able to work out that it's 6 pretty quickly as well if you didn't want to do the algebra. So we have to work out the value of this expression. Everything's already over a common denominator, so this is just the same as 6 minus 5 plus 4 minus 3 plus 2 minus 1 all over 12. Remember, BibMaths applies here. Common mistake people make is that they try to do, they do all the additions before the subtractions in something like this. But addition and subtraction in BibMaths, really it should be written something like this, B-I-D-M-A-S. A lot of teachers write it like this now because addition and subtraction have the same level of importance. So to work out something like this, I just do 6 minus 5 is 1, plus 4 is 5, minus 3 is 2, plus 2 is 4, minus 1 is 3, and so I get 3 over 12, and that gives me 1/4 once I've simplified it, and so the answer is C. 4 different positive integers have a product of 110. What's the sum of the 4 integers? The prime numbers are often referred to as the building blocks of arithmetic, the building blocks of numbers. It's because they really represent like the DNA of a number. So in a question like this, working out the factorization of 110 is really key. A lot of people do this with like a tree diagram here or something. So I've got 110, I could split that as 11 and 10, and then 10 I can split as 2 and 5 until I get down to prime numbers. So I know that 110 is equal to 2 times 5 times 11. Now it says that it's 4 different positive integers that have this product, but there's only 3 possible factors here, and if I start combining them, like 2 times 55, I'm going to have even less. So the other number we have to remember we can add in here is 1. So I could also write this as 110 is 1 times 2 times 5 times 11. Now I can't use 1 more than once, right? So I can't do something like 1 times 10 times 11 here, because then they wouldn't be different positive integers. So this is the only way we can do it. The numbers must be 1, 2, 5 and 11, and 1 plus 2 plus 5 plus 11 is 19, and so the answer is A, 19. So it says Wesley has a grid of 6 cells. He wants to colour 2 of the cells black, so the 2 black cells share a vertex but not a side. How many ways can he do this? So sharing a vertex but not a side means something like this, right? So it could be these two here, right? They share this vertex. A vertex is a corner, and then but they don't have a side in common here. So I can do those two, but I couldn't do those two because they have a side in common. Right, so let's start writing these down, and let's just find now to make sure we get them all, I'm going to go through systematically and start with everything that I can make with the first square, and then I'll know and then the next one, and then I'll know I've got them all if I do them systematically. I'll show you what I mean. So there's one possibility, right? I'm going to label those as a 1. Those two could go together. Right, now there's nothing else that can go with this top left square, right? Because the other ones it would share a side with. Okay, so if I look at the second square here, again, it shares a side with these two. It could, so we could share this vertex with this square, and that would be here. So that would be another option. Or it could go in the other direction here. So let me label that as 3 and 3. Okay, so that's options 1, 2, and 3. Now, if I look at this one that I've already labelled 2 here, that one could also go with the one underneath it here. So let's label that as option 4. But there's nothing else apart from the one we've already looked at. And then if I look at this middle square, well, that can go with the one it's already gone with, but everything else it shares a side with, so there's no more options there. And then this final one here could also go with this one, and then we can see we've exhausted all of the possibilities, and so the answer is D5. Notice how doing it systematically by starting at the top and working down in order there, I'm really confident that I've got them all and that there aren't any more. 1/2 of 1/3 of 1/4 of 1/5 of a number is 2. What is the number? Well, it's awkwardly phrased, but it's not a terribly difficult question. If we've just got to work back from 2 here, so if 1/5 of a number is 2, then that number must be 2 times 5, or 10, right? And then if 1/4 of 1/5 of a number is 2, well, that's saying 1/4 of of the number is 10 then, so I need to multiply by 4 as well. So I do 2 times 5 times 4, and then it's a third of that, so it's times 3, and a half of that is times 2. So if I take, 1/2 of this number, it would undo the multiplying by 2, a third of it undoing the multiplying by 3, a quarter would be undoing this multiplication, a fifth would be undoing this, and then I'd get 2. So this is the number that we want, and then we've just got to work it out. You can see then it's one of the bigger numbers, not the fractions. So I've got 10 times 4 is 40, times 3 is 120, times another 2 gives us 240, and the answer is A, 240. How many of these equations have the solution x equals 12? Well, let's just solve them one at a time. X minus 2 equals 10. Okay, if I add 2 to both sides, I get x equals 12. So that one does have the solution x equals 12. X over 2 equals 24. I'd have to multiply both sides of the equation by 2, and I would get x equals 48. So that one does not. For 10 minus x equals 2, if I add x to both sides, I get 10 equals x plus 2. And if I subtract 2 from each side, I get x equals 8. So that one does not have the solution x equals 12. And 2x minus 1 equals 25. I add 1 to each side to get 2x equals 26. And so x equals 13. So that one does not have the solution x equals 12. And so the answer is D, 1. This 3x3 grid shows 9 1cm by 1cm squares and uses 24 cm of wire. What length of wire is required for a similar 20 by 20 grid? It's just worth checking in these questions that you really understand what it means, and just check you can get this 24 cm answer from here, right? So it's saying, that all of the side lengths of these smaller squares are 1 cm. So if I added these together, I'd have 1, 2, 3, along the bottom here. So that'd be 3, 3, 3, 3. That would be 12. And then there'd be 3, 3, 3, 3, which is another 12. So I get 24 in total. And you see, checking that somehow gives you a bit of insight about the problem as well. Because if I extended this to a 20 by 20 grid and made this a lot bigger, I don't want to draw out the whole thing here, right? But you can see that perhaps I can do it a little bit more neatly than that though. You can see that if I want a 20 by 20 grid, right? Let's keep going. Let's just stop there. Right, so 3 by 3 grid, right, there were 4 vertical lines. If I go to 6 squares across, there's now 7 vertical lines. So there's always one more vertical line than there are the number of squares. So if I go to 20 by 20, right, there are going to be 21 vertical lines. And similarly for the horizontal ones, there's one more than the number of squares, 1, 2, 3, 4 here. And so there would also be 21 going up in this grid. Right, so actually what I need here is I need, but the actual length of each of these lines is still 20 centimeters, right? So here I had 4 lines of 3 centimeters, and I do that twice. So here I'm going to have 21 horizontal lines of 20 centimeters each, and I'm going to have 21 vertical lines of 20 centimeters each. So I add those together. So 21 times 20 is 21 times 2 times 10, which is 420. I'm going to have 2 of those, so 420 plus 420, or 420 times 2, that gives me 840 centimeters, and the final answer is E, 840. In question 12, we've got an equilateral triangle divided into 4 smaller equilateral triangles. So 1, 2, 3, 4 here. What fraction of the area of the large triangle has been shaded? Well, so you could say, okay, I've got 1, 2, 3, 4 triangles here. If you think about each of these, you can sort of break them down into very small triangles. And each of the sort of middle-sized triangles here has 4 of the smaller ones, and there's 4 of them. So there's 16 of these small triangles in total, 3 of which are shaded. So the answer is that the shaded area is 3 out of 16, and the answer is B, 3/16. You could also just look at the middle triangle and say, well, it's 3/4 of the middle triangle, and the middle triangle is 1/4 of the large triangle, so it's 3/4 times 1/4, or 3/4 divided by 4, which again gets us to 3/16. Here we're told the mean of 4 positive integers is 5, and the median of the integers is 6, and we want to know what's the mean of the largest and the smallest of the integers. Now, when you've got a list of 4 numbers, right, these aren't the actual numbers, but let's say it was 4, 11, 17, and 23, right, the median of them, you take the average of the middle two, because there is no middle value, right? So I have to work out 11 plus 17 over 2 here and get that 14 is the median. So actually the median of the integers is the mean of the middle two numbers, right? So if I've got a, b, c and d, the median is the mean of b and c, but it's also the mean of b and c. So that means that b and c must add together to give 12, and then 12 divided by 2 would be 6, right? So we've got b plus c is 12, but the mean of all of the integers is 5, so that would mean that a plus b plus c plus d must be 20, because that's 4 times 5, right? If the mean is 5, the total is 4 times. So that must mean that the other two, a and d, must add together to give 8, because the middle two add together to give 12, and in total you've got 20. So if they add together to give 8, their mean is 8 divided by 2, which is 4, and so the answer is B, 4. It says in the diagram angle OLM is twice as large as PON. So in this sort of question, the first thing I would do is I would just label those, right? So twice as large as PON, so PON will make that one X, and OLM, this one here, well, that's twice as large, so let's call that 2X. And then just start filling in anything you know. Okay, we want to work out what this OLM is. So this angle in here is 180 minus 124, that's 56. And okay, these are opposite angles, so that one would also be X. And now I can see that I can sort of work it out based on this triangle here. Let me just see if I can write that a bit more clearly. Maybe if I don't draw that angle, I can write X. So this angle here is 180 minus 2X, but it's also 180 minus 56 minus X because of the angles in the triangle, right? The angles in the triangle say that 56 plus X plus this unknown one here, why don't I just give it a name, let's call it Y, is 180, but it's also that 180 minus 2X is equal to Y, right? So so it must actually be that this 2X is the same as 56 plus X, right? Because what I'm saying here is that Y is 180 minus 2X, but Y is also 180 minus this 56 plus X. Okay, so either way, you know, it's 180 minus 2X, or it's 180 minus 56 plus X, I get the same thing. And there's also a result about triangles that you might know that, you know, this is always the case, right? If you've got a triangle, this sort of exterior angle here is always the sum of the other two angles. That's something I go through in the full Go for Gold in the JMC course, actually. And so you could just go straight to 22x equals 56 plus x if you knew that fact. Anyway, so we get subtract x from each side, and so we get that x is 56, and it asks for OLM, which is 2x. So 2x here is 112. And the answer is D. So there'd be different ways of writing down the answer here, but this is a pretty classic Venn diagram sort of situation for me. So I'm going to draw a Venn diagram, and what this means is that I've got either tennis here or football, and in this diagram, you know, being in the just here means you just play tennis, here it means you play both, and here it means you just play football. So there's 42 children in total, so the same number play tennis as just football. That's a little bit hard to write down, as you'll see, because I'm going to start with twice as many people play both tennis and football as play just tennis, because both tennis and football is a distinct region in this diagram. So if we have, let's say, X people that play just tennis, then twice as many play both tennis and football. So I could put those 2x in here. And now you see the total number of people that play tennis would be x plus 2x, which is 3x. Now, if we go back to the first piece of information, the same number play tennis as play just football, so the total that play tennis is 3x, so there must be 3x that play just football, and so that was the total for tennis, and the total for football then would be 2x plus 3x. Right, that's people that play just football or play both tennis and football, so that would be 5x. Right, now we know that in total here, look, there's x plus 2x plus 3x students, and that there are 42 children in total, so 6x is 42, so that means that x must be 7, and then the 5x, the number that play football, is 5 times 7, so that's 35, and the answer is E, 35. Question 16, you're given the sequence of digits 0, 6, 2, 5, and you're allowed to put a decimal point either at the beginning, the end, or in any other position. So we can have 0.0625, we can have 0.625, we could have 6.25, we could have 62.5, or we could have 625. Okay, you know, when you can think of there being zeros at the front here, but that would be all the possible options. And it says, which of these numbers can you not make? Well, if we go through them one at a time, 6/25, that would be 24 over 100, and so that's not any of these. So actually, I can just say that the answer is A. We might want to check all of the others. 5/8 is 0.625. 1/16, you might know that 1/8 is 0.125, and if you do half of that, like half of 125 is 62 and a half, so you would get 0.0625. 25 over 4, that's 6 1/4, so that's 6.25, and 25 squared is 625, so we can make all the others, and the answer is A. The next question, we've got this rectangle that's dissected into 9 different sized squares as shown in the diagram, and so really what we've got to do here is work out which length is which, and it's not too bad here, right? So clearly the smallest one here is the one, the shaded one in the middle, right? And the next biggest one, 4, is this one. This will be 4x4, and then the one that's the next biggest here is going to be 7. So this one looks like it's the next biggest, doesn't it? And then the next one is 8, and you can sort of see, well, okay, if I do 7 along the bottom here plus 1, that gives me 8. So this one is 8, and again 8 plus 1 gives me 9, so that one's definitely 9, and then 9 plus 1 is 10, so that one's 10, and then 10 plus 4 is 14, and then 14 plus 4 is 18, and then this last one must be 15, and that's 7 plus 8, which is 15. Okay, now if I want to work out the area of the rectangle, and if we look along the sides, so this distance here is 18 plus 15, that's 33, and you can double check that that's the same as 14 plus 10 plus 9 going down the other side if you want to, and along the top 14 plus 18 is 32, and you can check that's the same as 15 plus 8 plus 9 if you want to be sure. So we've just got to work out 32 times 33 here. You can do that as a long multiplication if you want to. I happen to know that 32 times 32 is 1024 quite easily, and I know that because I know my powers of 2, and that's really useful to know, right? So 32 is 2 to the power of 5, and if I do 2 to the power of 5 times 2 to the power of 5, I get 2 to the power of 10, which is 1024, so it's a good sequence to know. And we actually want 32 times 33, so that's going to be another 32 on top of this, so that's 1056, but you know, do the multiplication however you want, obviously. Either way, the answer is E, 1056. How many 2-digit primes have both of their digits not prime? Okay, so which digits are not prime? Well, 1 is not prime, 2 is, 3 is, 4 is not prime, 5 is prime, 6 is not, 7 is prime, 8 is not, and 9 is not. So it's actually saying how many 2-digit primes can we make up from these numbers. So let's narrow down our search a little bit. And remember, a 2-digit prime is, we've only got to check whether 2, 3, 5 and 7 are factors or not. I go through that in detail about why that's true in the full course, Go for Gold in the Junior Maths Challenge. So I'm just going to check these out here. So I'm going to look at the things that start with 1 first. So 1 then something. Okay, so it could, and I can only choose between these. Now 11 is prime, 14 is not, 16 is not, 18 is not, and 19 is prime. Okay, then I look at things that could be 4 something. 41 is a candidate to be prime, doesn't have 2 as a factor or 5, and its digit sum 4 plus 1 is 5, so it's not a multiple of 3, so it is prime. Maybe you also just know it's prime. Anything that ends in an even number I can always rule out, of course, as well, right? So I really only have to check, you know, the things that end in 1 or 9 here, right? So it's 49 prime. Well, 49 is 7 times 7, so that's not prime. So then I just check the things that are 6 something, so I just need to check 61 and 69. 69 is obviously a multiple of 3 here, and 61 is prime because, again, it doesn't have 2, 3 or 5 as a factor. If I look at the 8x's, that's 81, well that's 9 squared, so definitely not that. and 89 here, again, that doesn't have 2, 3, 5 or 7 as a factor here, and you can just check all of those. Sorry, I should have checked 7 for 61 as well, but it's obviously not a multiple of 7, so that's a prime. And then for 9x, I've got to think, well, is 91 a prime? That is doesn't have 2, 3 or 5 as a factor, but it is 7 times 13, so that's not prime. And 99 is 3 times 33, so that's not prime. So we've exhaustively searched them all, and there's 1, 2, 3, 4, 5, and so the answer is B5. In the answer I just gave, by the way, I didn't include the number 0, and I just wanted to add a little addition here to say why that wasn't the case. Of course, 0 is also a digit that's not prime, so you could include it in a number if you wanted to, but clearly no number that starts or ends with a 0 can be prime, so it's not going to be in any of the answers, which is why I ignored it. Okay. So the table's shown the sum of each row is equal to the right of the row, and each sum of each column is shown below the column. So that means like j plus k plus j is 5, k plus k plus j is 7, and there's different ways you can work out the answer here for sure. One thing I notice is that if I look at this row, that would mean that 2k plus l is 13, and if I look at this column, 2k plus j, right, is only 7. So actually that means that l must be 6 bigger than j. Now, assuming these are all like positive integers, then I could probably just say straight away, well, if l is got to be 6 bigger than another integer, well, j's 1, then l's 7, right? I mean, so actually I might just go with that and say I think j equals 1, l equals 7, and then I can work out, well, that would mean that k would have to be 3, and you can just sort of verify that it does work in this table. So a good maths challengey way of doing it there is at that point just to say, yeah, we know e is 7. If you don't want to do it quite so sneakily as that, of course, we could put those together and say, well, I know this means that L is j plus 6, and then I could just find a column that just has j and l in it, so like this one here, and I can say j plus 2l equals 15. Well, if l is j plus 6, then j is l minus 6. And if I substitute that in here, I get l minus 6 plus 2l equals 15. So 3l is 21. And so again, then l is 7, as we found before. So you can deduce it absolutely for sure there. But it's the maths challenge, you know, part of the game we're playing here is to try and get through the questions quickly and use whatever tricks we can to give ourselves time to think about the later questions. Question 20, it says Edmund makes a cube using 8 small cubes. So just let's start by thinking about that. So if it's made of 8 small cubes, then the cube itself is going to look something like this. It's going to be 2 by 2 by 2, and that would be 8 cubes. So we take the cube root of 8 basically to get 2. And then Samuel's making one with the same size small cubes, but his is going to be twice as long, so it's going to be 4 this way, 3 times as wide, so it's going to be 6 this way, and it's going to be 4 times as high, so it's going to be 8 up. And we want to know how many more cubes does Samuel use than Edward. Right, well, so clearly Samuel's then is a 4 by 6 by 8, which is 24 times 8 small cubes then. So that's 20 times 8 is 160, plus 4 times 8 is 32, so that's 192 cubes. You can do it by a long multiplication if you prefer. So Edmund used 8, so 192 minus 8 is how many more Samuel uses. That's 184, and so the answer is D. Question 21, it says the digits of both the 2-digit numbers in the first calculation have been reversed to give the numbers in the second calculation, but the answer stayed the same. So 62, they've swapped the digits to get 26. 13, they've swapped the digits to get 31. We want to know which of the calculations give the same thing here. So in A, it would be 52 times 63, right? Now, I don't need to do the calculation to know that these are not the same, because I know that multiplication preserves the last digits. That's another idea that I go through in one of the introductory videos in the full course, Go for Gold in the Junior Maths Challenge. Here I just check 5 times 6 ends in with 30, ends in a 0, 2 times 3 ends in a 6, so they can't be equal. Right, 34 times 42, that will turn into 43 times 24. 4 times 2 is 8. 3 times 4 is 12. They don't have the same last digit, so they can't be equal. 54 times 56 will become 45 times 65. 4 times 6 is 24. 5 times 5 is 25. Don't end on the same last digit, so they can't be that one. 42 times 48. 24 times 84 is what we're looking at here now. 2 times 8 is 16, 4 times 4 is also 16, so this one's a possibility. The last digit thing is only going to rule things out here, so I've either now got to check that these are actually the same, or I could just look at the last one here. 23 times 34, 2 times 3 is 6, 3 times 4 is 12, don't have the same last digit, so it must be D. And then you can also look at D and say, well, yeah, that is right, because look, 48 is double 24, and 84 is double 42, so those calculations are going to give the same thing. Either way, the answer is D. Harriet has a square piece of paper. She folds it in half to form a rectangle and then in half again to form a second rectangle, which is not a square. It says the perimeter of the second rectangle is 30. What's the area of the original square? Okay, so this thing about the it not being a square is really important here, right? So imagine you fold this square in half, and then it would look. I just have the bottom half here. Now, if I fold it in half again along this line, I end up with a square. So that's not how we're meant to fold it. We're meant to fold it again in like this line here. So what I'm left with is just this bottom part here. Okay, so that means that you can see that whatever the side length of the square is, the side of the rectangle we end up with here is a quarter of it, right? Because it's this would if that's the full side length, that would be a half. That would be a half. Half here, and then that would be a quarter of it. Now, rather than doing x and a quarter x here, it's easier to do x and 4x. So if you want a quarter of something, make the something is a quarter of 4x. And then you can see the perimeter of the rectangle we're left with here is 4x plus 4x plus x, which is 10x. So 10x is equal to 30. That means x equals 3. So 4x is equal to 12, and this square is a 12 by 12 square then. So the area of the original square is 12 times 12, which is 144. 23, it says there's more than one integer greater than 1 that leaves a remainder of 1 when divided by each of the four smallest primes. So we need to remember what those are. That's 2, 3, 5 and 7. Remember, 1 is not a prime. And it says what's the difference between the two smallest such integers that are one more than a greater, that leave a remainder of 1 when divided by each of these. So because these numbers don't have anything in common, the smallest number this is going to be true for is 2 times 3 times 5 times 7 plus 1. Okay, you see that if I divide this number by 7, then like this bit is a multiple of 7, so I'd get an exact division when dividing that by 7. So if I add 1 to it, then I'd get a remainder when dividing by 7. And you can make that argument for 2, 3 and 5 as well. If I divide it by 2 here, this is an exact multiple of 2, so I'll just get this as the remainder. So that's how we'd construct this. 2 times 3 times 5 times 7 is 6 times 5 is 30, times 7 is 210, so this is 210 plus 1. Right, so that's 211. Now the next number that this would be true of would just be not double the whole number, but if I did two lots of 2 times 3 times 5 times 7, I could make the same argument. This is now the next thing that's a multiple of 2, 3, 5 and 7. So if I add 1 to it, it's the next thing that leaves a remainder of 1 when divided by all of them. So you can either just jump now and say, well, the answer is 210 because this is 210 bigger than this one, or you could actually write down that this is 421, and then 2421 minus 211 is 210. But either way, the answer is B, 210. Okay, so it says Susan's attending a talk at her son's school where 8 rows of 10 chairs where 54 parents are sitting. She notices every parent is either sitting on their own or next to just one other person. What's the largest possible number of adjacent empty chairs in a single row at that talk? So this is one of those sort of problems where we're always just trying to like stretch the situation to give like the worst or the best case scenario depending how you're thinking about it, right? So imagine this is just one of the rows of 10 chairs, and I want to try and put like as many parents in this row as possible. So that I can say, oh, let's fill up the first 7 rows as much as possible, and then we'll think about the last row and see like what the most space I can leave in it is. So if I've got 2 sitting next to each other or 1 sitting next to each other, that's the only possibility. I'm going to want to put as many 2s next to each other as possible so I don't leave too much space, right? So I could put 2 parents here, I could leave a gap, I could put 2 here, I could leave a gap, put 2 here, I could leave a gap and put 1 here, right? And really that's the that's the smallest gaps I can leave here. Obviously I never want to leave a gap on the very end because that's just a wasted gap, and if I start with 2 on the end or 1 on the end, I'm going to end up with the same configuration here. So I could put these 3 gaps anyway here, as long as I have 3 pairs in a single, but there's going to be 3 gaps. So in a particular row I can get 7 parents in a row, right? So I've got 7 parents, and if I put 7 parents in each of 7 rows, then that's 7 times 7, which is 49 parents in those rows. So that leaves 5 parents for the last row, and this is the one where I'm going to try and design the biggest gap possible. So again, I could try and put 2 next to each other here on the side, I have to leave a gap, put 2 next to each other, leave a gap, and then I've got to put 1 somewhere. Now that leaves a gap of 3 here, and I just sort of think, is that the best I could do? Is there any way of playing around with this? Well, actually, of course, if I, at the moment I've got this gap here, if I put that last parent on the end instead of here, then I get a gap of 4. And if you play around with this, there's now really no better way we can do this. That's really optimized the situation. I mean, try playing around with it if you're not sure, but that's the best. And so the maximum possible of adjacent empty chairs there can be is 4, and the answer is B. Just put question 25 on the screen here, and I've just made a bigger copy of the diagram to make it a bit easier to look at. That's always a good thing. If you get a bit stuck on these problems, maybe try drawing a big version of the picture out. It can help you fill things in more nicely. We're told that these are straight lines, PQRS, JQK and LRK, just in case we had any doubts there. And we want to work out the angle JKL, so that's this one in here. Now, so let's just start filling in the more obvious things we can see in here. Well, I've definitely got some opposite angles. So if this is 2y, then this one is equal to 2y. And if this one is 2x, then this one's equal to 2x. So actually I notice here that the answer to the question here from this triangle is 180 minus 2x minus 2y. So actually it might be one of those questions where I don't end up working out what x and y is. I just work out what 2x minus 2y is here, right? So, and in fact I can write that as 180 minus 2 times x plus y. So I see here, if I can work out what x plus y is, then I can work out the answer to this question. And I've got another triangle here and some straight lines that I haven't used. So if I think about this angle A here, and then look down this straight line, A is 180 minus x minus 2y. Also, if I look at this angle B, B is 180 minus y minus 2x, looking along the straight line that B is sitting on here. So I also know that angles in this triangle QMR add up to 180 degrees, so it must be that A plus B plus 33 is 180. So I can put this all together here, everything below this line. So if I put A and B in here, that means that 180 minus x minus 2y plus 180 minus y minus 2x, okay, that's 180. Plus 33. So I've got to add the 33. Plus 33 is 180. Okay, so I can make the things a bit easier here. I can subtract 180 from both sides, and then I can just combine everything that I've got here. So 180 plus 33 is 213, and then I've got minus 3x minus 3y equals 0. So 213 is equal to 3x plus 3y, adding the 3x and the 3y to both sides. So that means that if I divide by 3 here, 213 divided by 3 is 71, and 21 times 3 is 7 times 3 is 21, so 70 times 3 is 210, so 71 times 3 is 213. You can do this in your head, or you can do it as a division, whatever you prefer. Anyway, dividing by 3, we get 71 equals x plus y, and now I realise I don't need to know x and y, right? All I wanted for the answer here was to know that the answer is 180 minus 2 lots of x plus y. So the answer I'm looking for is 180 minus 2 times 71, because that's x plus y. 2 times 71 is 142, so this is 180 minus 142, and that gives me 38, and so the answer is E, 38 degrees.